So we've talked about Newton's laws of motion as well as Newton's law of gravity. However, there are other laws that can also help us predict and understand what's going to happen around us. Most of these are referred to as conservation laws. Now, what do we mean by conserved? It means that the amount does not change in time. Okay, the total amount remains the same. So some things that are conserved, we have mass, momentum, angular momentum, and energy. Probably the one of these that you're the most familiar with is conservation of mass. Okay, so for example, imagine you've got a donut. You then eat that donut. After eating the donut, is the donut's mass gone? Is it destroyed? Absolutely not. What's happened is that the mass of the donut has transformed from mass of donut into mass of you. Okay, so if you were to weigh yourself after on a very precise scale, you would actually see that your weight or your mass has increased by the mass of the donut. Mass is not created or destroyed, but it can transform, it can transfer from one object to another. Okay, so some other quantities that are conserved, we have momentum, angular momentum, and energy. We've actually talked about momentum previously. Remember, this is the inertia of motion. Once something is moving, it wants to keep moving. This is the idea of momentum. Now, assuming that there are no outside forces, momentum or linear momentum is actually conserved. And you've probably actually seen this before at some point. Okay, so for me, kind of a thing that I've seen is it's called a Newton's cradle. Okay, the place that I've seen it depicted most in like movies and TV shows is on the desk of a psychologist or psychiatrist. Okay, but it's the hanging balls. You got 4 hanging balls. You raise one up, it falls down, hits, and then the ball on the other side swings up, and they go back and forth. That's called a Newton's cradle, and it actually shows conservation of momentum. The idea is that ball on one side is going to be traveling quickly. When it hits, the momentum then travels through the balls until the ball on the end then flies up. So the momentum is transferred from one object to another, but the total amount of momentum is remaining the same. A similar thing can actually be seen with pool balls. Okay, so in this case, we have the white cue ball and a yellow ball. Notice that the yellow ball is not moving at all. If you hit just right, then all of the momentum will transfer from the cue ball to the yellow ball. The white ball will stop, and the cue ball will zip off at the same speed that the white ball used to have. In other words, the starting momentum is going to be the same as the total ending momentum. This is the idea of conservation of momentum. Something else that is conserved is angular momentum. Angular momentum is kind of like momentum, but it's for spinning things. Momentum is straight line motion. Angular momentum is rotational motion. So if something is rotating, it wants to keep rotating. It's the motion of rotation. Okay, the angular momentum is the object's mass times its velocity times its distance. Okay, now this distance is from what it's rotating around. So if we're looking at a rotating disk, it's from the center of the disk out to the edge. If we're looking at a planet orbiting around a star, then it's the distance from the star out to the planet. That's the distance. Now, related to a force is a torque. A torque is a twisting force, and this is what changes angular momentum. Now, we can actually see the conservation of angular momentum in action as we look at a figure skater. Okay, so hopefully you've seen a figure skater before. So we have our figure skater, and she starts out her spin with her arms out wide, and she starts spinning relatively slowly. However, as she draws her arms in, then she speeds up. So let's take a look at what's going on. Okay, as she is doing this, there are no torques, so the total amount of angular momentum must remain the same. We're also going to assume that her mass is going to remain the same. Just rotating, just spinning, probably shouldn't change her mass. Every time I've thought about how it is that your mass could change because you're rotating, it ends up in a bad situation. So we're going to assume her mass is going to remain the same. So the only two things that can change are the radius, the distance from her center out to the edge, and her velocity. So angular momentum and mass remain the same. So she starts out, her arms are out wide, and she spins slowly. Then she draws her arms in, which means this distance decreases. To make sure everything else stays the same, her speed then must go up. Okay, so she spins faster. Then at the end of her spin, she puts her arms back out. The distance increases so that the velocity then must decrease. Okay, this is what we see from conservation of angular momentum. Okay, this also helps us explain Kepler's second law. Okay, so again, notice we're dealing Kepler and not Newton. Kepler is all about planetary motion. Kepler's second law states that as planets orbit around the sun, they will speed up and slow down. Okay, so here we have the Earth, and we start out far away, and it's traveling relatively slowly. As it moves in towards the sun, the distance decreases. Because the distance decreases, the speed must increase. So as the Earth gets closer to the sun, it has to speed up. Then, as it starts to get farther from the Earth again, then our distance increases, so the speed must decrease. So the farther away it goes, the slower it goes. Then as it gets closer, the faster it goes. So we get this speed up and slow down because of the elliptical orbit. All of this is just a consequence of conservation of angular momentum. Now, this is not something that Kepler realized. He just knew that this had to happen to have all of the data that he had work out correctly. But we now know why. It's conservation of angular momentum. Now, conservation of angular momentum also helps us explain why it is that the Earth keeps rotating and the Earth keeps orbiting around the sun. There are no torques on the Earth, so angular momentum remains the same, so the Earth keeps rotating and it keeps revolving around the sun. This also helps us explain why there are so many disc-shaped objects in the universe. And so imagine we've got a giant cloud of gas that is rotating slowly. Then, as gravity pulls on it, it begins to shrink. However, in the plane that it's rotating in, we have conservation of angular momentum, so it starts to rotate faster. Because it's rotating faster in that plane, we have the momentum that tries to keep things pushed out. Think about driving in a car and taking a fast corner. You feel that push out of the car. Technically, there's no actual push, it is just inertia. You want to keep going in the same direction, there's other forces trying to make you go other directions. In the direction that it's rotating, it's going to stay kind of pushed out because of this. But in the direction that it's not rotating, gravity's able to keep pulling it, and so it keeps settling down until it forms a broad but narrow disk.